warm welcome indeed to anyone joining. Thank you for being here. Get yourself ready with a notebook, grab a pencil or a pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have an exploration on a calculus topic that is looking at the rectangle approximation of areas. One of the things that makes calculus really useful, which is much different than any level of math beneath it, is that calculus allows us to model things which are constantly changing. Calculus allows us to sort of keep track of accumulations, even if they're not constantly changing. So here I have a little sketch. I'll resketch it, make it curvy. And here's a piece of a function. If we want to find the area underneath, which is equivalent to determining the accumulated value of the function over a certain interval, it would be tough to do this with any previous methods because we only have geometric shapes. Like we can maybe make a rectangle here and then try to make some kind of a triangle and say that almost cuts it. That's pretty much the area. We can find these values, these heights and such, but it wouldn't be an accurate representation. However, if we make some rectangles in a slightly clever way, if we kind of make one rectangle and then make another rectangle, that area could possibly be a lot closer to the area underneath. I'm still missing some, right? I'm still missing all of this, and I actually counted this over. So it's also probably not the most accurate. But as you can imagine, hopefully you can imagine this, if I make more, rather I should say I want you to imagine this, if I make more rectangles, they still be the same width as each other, but they'll be a little skinnier than when I only made 3 rectangles. If I make more of these rectangles, then the area underneath these rectangles, or inside of these rectangles, is getting a lot closer to the true area. So this video is intended to show you how left and right rectangle approximations work. Okay. So again, we're going to take a look at our friendly function. And here we're going to look at something called left rectangles. Now I need to be really clear what I mean by left rectangles. They're obviously different from right rectangles, but how are they different? Well, on each of these rectangles, we have a width, and it's the same width for every single rectangle. Delta x, delta x, delta x, delta x, delta x, so on and so forth. The area of one of these rectangles is just the base, which is the width, times the height. I know I made this rectangle a little bit fatter than the other guys, but let's just pretend they're all the same. So the area for these rectangles is basically going to be whatever the height is here. So let's call this f of a times delta x, right? That's the height times the width, delta x. Plus, what about the next rectangle? What is the height here? What is the height of that rectangle? Well, this is f of a plus delta x. That's not very specific, but what I'm saying is that if we start at the value a and then go forward by delta x, I'll be on this new rectangle, and the left endpoint has a height of f of a plus delta x. So we're going to add f of a plus delta x. That's a new function value with a different height. In fact, I'll leave that in red, I think. Yeah, I'll leave this in red. F of a plus delta x, and this is also times delta x. And the process continues until we get to the last rectangle. So this is going to be f of a plus n minus 1 times delta x. Why is it n minus 1? Well, how many rectangles did we have to jump to get there? We started on the first one, and when we got to the second one, we just had to add delta x. And when we got to the third one, we had to add 2 delta x. And when we got to the third one, we had to add, the fourth one, we had to add 3 delta x. So as we go on, this left endpoint is a plus n minus 1 times delta x. That's right before we get to the b. B is the final number, but we're not going to go all that far because we don't need the right side of that rectangle. We just need the left endpoint of this rectangle. And then, of course, we're going to multiply that by delta x, and that gives us the area of that rectangle. Okay, now what about the right rectangles? Well, the right rectangles, you can see that these are going to be an overestimation, and that's because we're starting off with this height. We're not starting at f of a. We're starting off at f of a plus delta x. We already moved forward one rectangle, and that's the height that we're getting, but we still have the same delta x for the base on all of these rectangles. So what you need to do in a problem is you need to find the function values at each of these little spots. Let's pretend that we're going from -2 to 4, and we have n equals 8 rectangles. You would have to know the function value. First of all, how much is each delta x? Delta x is going to be the b minus a divided by n. So it's the whole space of the interval divided by however many rectangles I've divided it into. That's pretty straightforward. So here we're going to have delta x is 4 minus -2 over 8, which is 6 over 8, 3 over 4. Okay. So that means we're going to need to know f of -2, f of -2 plus 3/4, which is going to be -5/4. We need to know f of, add 3/4 again, -2/4, which is -1/2. We need to know f of 1/4. We need to know f of 1. We need to know f of 7/4. We need to know f of 10/4, which we can just call 5/2. We need to know f of 13/4, and we need to know f of 16/4, which we just call 4. So we need all of these heights of the rectangles, and I'm going to show you how to use Desmos in order to quickly get that. Because if you're given a problem like this on the AP Calculus exam, and the numbers are not working out extremely nicely, and they're asking for a large amount of rectangles, then you'll definitely need to save time by using Desmos, some kind of graphing calculator. So we'll look at the examples on this graphing calculator. But for now, I just want you to know how to break up the interval into n rectangles. You take the interval from a to b, and the size of that interval is b minus a. You divide this by n, which gives you the width of all of the rectangles. So I would basically say the area under the curve is going to be f of -2 times the width of 3/4 plus f of -5/4 times 3/4, that's the width. And I would do this for the left rectangles. I'll say left area. And for the right rectangles, for the right area, I would be starting off at f of -5/4 times the width 3/4, but I would make it all the way to f of 4. So I would make it all the way to the right endpoint, whereas on this left sum, I would only make it up to f of 13/4 times 3/4, because that would get me on the last rectangle and put me on the left endpoint of the last rectangle. But if we want a right sum, we need to go to the end of the right endpoint on the last rectangle. Okay, so let's look at some examples. I'd like you to try these on your own if you get a chance. Pause the video and try them both. We have L4 for this function and R4 for this other function. So L4 for f of x equals 1 over x minus 1. What we want to do is we want to start off at 2. So our sort of like our x0, you can call it, is 2. How far forward are we going? Well, b minus a is 3 minus 2, and the number of rectangles is 4. So we have 1/4. So if we go forward by 1/4, we end up at 9/4. All right, let's keep going forward by 1/4. That's 10/4, or 5/2. Then we have 11/4. And then we finally have 12/4, which we could just call 3, right? Those are all of our function values. If I want L4, I only want to make rectangles from these 4 points. So that's going to require me to figure out what is f of 2 and what is f of 9/4. And of course, this could be done by hand. I do encourage you to try it by hand. But I also want you to sort of try it. That way you can see just how long it takes, and then you can use Desmos and see how much time you're actually saving, right? This will be -1. Oops. That'll be 1/1, which is just 1. This would be 1/5/4, which is 4/5. This would be 1/3/2, which is 2/3. This would be 1/7/4, which is 4/7. And this would be 1/2, which is just a half. Now, if you need to use Desmos for that, here's how you do it. Y equals, make a fraction out of this, 1/x minus 1. Go to your settings gear, you see that? Or edit list gear. And then go to table. If you create the table, you can plug in whatever values you want. So we can start off with 2, and then 2 1/4, so 2.25, or if you want to put 9/4, that's fine. Then we have 5/2. Then we have 11/4. Why do I feel like I messed that up? 13/4, right? Shouldn't that be 13/4? Oh, no, 11/4. Next is 12/4. Got it, which is just 3. Little confusion there. So here are the points that we have. And if we want to make rectangles out of these, it's actually very easy to find the sum of these rectangles. Remember that we're only using the top 4 points here. So you're going to put, I guess I can call this f of x. There we go. So now we can say f of 2 times 3/4. No, times 1/4. That's the width. Plus f of 9/4. And you don't even need to make a table to do this, actually, but I'm just being thorough, showing you how you can make a table and write it out, and how you can simply plug it into the calculator of Desmos. As long as you're plugging things in accurately, you'll be totally fine. Times 1/4. Plus, here's the last one, 11/4 times 1/4. And so this is our approximation of the area underneath that curve, 0.7595. If you were doing this on the AP Calc exam, it'd probably be acceptable for you to say 0.760. I think that's fine. And if you take a look at the graph, all of those rectangles would go straight across. So here, I'm going to take a screenshot and post this on the grid, on the whiteboard. If we take a look at this, and we try to estimate whether or not this would be an overestimate or an underestimate, just look at the rectangles that we're creating. They sit above the curve, and that's actually because the curve is concave down. Side note. But they sit above the curve, so this is an overestimate. We know that the actual area underneath the curve from 2 to 3 is a little bit less than that. All right, let's finish up with R4, which is just the graph of a parabola. It's pretty easy. Let me clear this up and plug in our new function, x squared. Oops. I believe it's minus 2x plus 1. Is that right? Minus 2x, yes. Okay, so what points do we need? Well, here's our b minus a. And we want 4 rectangles again. So the width of each rectangle is going to be 1/2. that means that we start off with f of 0, and then we go forward by 1/2 at a time. F of 1/2, f of 1, f of 3/2, and finally f of 4/2, which is just 2. There we go. So we're going to take these 4 because we're doing a right rectangle approximation, and we can easily plug this into the calculator very directly. Let's go ahead and do that. So we're going to start off with f of 1/2, and we're going to multiply that by 1/2. Then we're going to do f of 1, and we're going to multiply that by 1/2. Then we're going to do f of 3/2, and we're going to multiply that by 1/2. Oops. I forgot to add that. There we go. And I just deleted it. Good old Control Z. Plus f of 4/2, which is just 2, and this is also going to be times 1/2. So the approximation here is 0.75. And if we take a look at these points on the grid, we do need an actual table for that. So let's say 0, 1/2, 1, 3/2, 2, 2. And as you can see there, if we take a screenshot of this one, this is a different graph, by the way, so we're not talking about the same one as last time. These rectangles are right rectangles, so they exist above the graph here. This one's actually a 0 rectangle. See that? Because this, for the rectangle that would be right here, the right side is just 0, so that doesn't even contribute any area. And then this one is a slight underestimate. So it's possible that what's missing here and what's overestimated here, what's missing here and what's overestimated here, it's possible those things kind of balance each other out a little bit, but this is very likely still an overestimate, by my guess. Although, who knows? Might be very, very accurate here. What did we say it was? We said that R4 was approximately 0.75. So this is how you use Desmos to calculate things very quickly. Otherwise, you would have to write this entire expression out and evaluate the function for yourself at each of these points. So be happy that the calculators are here. They definitely make life a little bit easier, right? I think that's enough blab out of me. I'll see you guys next time.